Imagine this. You follow the hottest trend of 2024 and buy a robot. Aside from its attractive pre-computed capabilities, like the ability to fold clothes, or cook you a bowl of soup, or stage a rebellion at work, you yearn for something more, something a little more personalized to your unique needs, more malleable, teachable, a bit more human. But what exactly does a human-like robot mean? When we think about the future of robots, we envision a mechanical genius powered by a digital superintelligence that has the ability to automate pretty much any task. But in order to meet up to these expectations, our robots need a brain. Not just any brain, but a brain that has the ability to learn on the go, and most importantly, self-improve. This brain must be multimodal with the ability to consume information in all possible formats. It must have the ability to simultaneously reason across multiple modalities, forming conclusions by considering multiple information streams. It must be able to reason spatially and make decisions by choosing from multiple viable decision pathways. And most importantly, it must be able to consume very long streams of information without collapsing into a processing overload mess. At this point, you might be wondering, what could possibly be the best candidate for this brain? Enter Gemini 1.5 models and their superpower, multimodal long-context reasoning. To teach our new brain anything in real time, we created a very simple yet scalable universal system for Gemini 1.5 models. First, we created a navigation guide by dividing images and videos into discrete numbered sections using a grid overlay, a process called spatial discretization. This gives Gemini its own unique navigation language, allowing it to communicate its understanding of physical movements. Next, we created the concept of equivalence, information about object parts learned during training that transfers to similar tasks. For example, a robot learning on one coffee machine should be able to identify equivalent parts on different machines despite substantial variations between them. This universal system, combined with Gemini 1.5's long context reasoning, means having a Gemini API is like having a superhuman brain that can learn and replicate any spatial visual task on the go, without additional machine learning. Okay, let's stress test our system. To do this, we challenged Gemini 1.5 Pro with one of the most intellectually demanding tasks requiring long context reasoning across multiple modalities, performing an urgent, life-threatening appendectomy surgery. First, we fed Gemini a video of the surgical operation along with extracted keyframes with numbered grid overlays. We then gave Gemini the following tasks: compute anatomical equivalence to the content of each grid, compute the sequence of movements across grids throughout the surgery, compute the type of movement, whether it's a left or right movement, compute the angle of the surgical equipment during the movement, and compute the force applied during each movement. The output? A sequence of movements and movement types across grids, ready for conversion to robotic motor commands. Context caching plays a very important role here, as it enables recursive self-improvement, which is crucial in high-stakes scenarios where errors could be fatal. With very minimal prompting, we found that Gemini 1.5 Pro excelled at the given task. While there's room for improvement in grid navigation, especially for tasks requiring much smaller grids, its ability to reason across multiple modalities and generate actionable instructions from newly learned tasks suggests that by next year, we may see Gemini 1.5 powered robots capable of learning and automating any task in real time. The best part? For this project, we only tested Gemini as the part of the brain that performed spatial visual reasoning, but here is where it gets really exciting. Gemini's use could be further extended to process real-time screenshots of the surgical environment. The same number of grids will be overlaid onto these screenshots, matching the exact navigation pre-computed earlier using Gemini's new navigation language. This means that Gemini 1.5 models are not only capable of providing spatial reasoning input for conversion into motor commands, but can also mimic the motor system part of the human brain to replicate the surgery in real time. With Gemini's multimodal long-context reasoning capabilities, reaching the long-awaited future of on-the-fly learning and text-to-action is right around the corner. All Gemini needs is a body and a simple code.